Hello everyone, welcome back. So, let us continue our discussion on 2D stress field. If you recall, we last discussed Mohr circle, right? Okay, so we have a 2D stress field. As you can see, in this case we have sigma x and sigma y in two orthogonal planes. So, this is sigma xx and sigma yy. We also have shear stress tau is tau xy and given this configuration we can evaluate what is sigma n, that is the normal stress at a particular plane. So, that is sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 cos of twice alpha plus tau xy sin of twice alpha, and then tau n is equal to minus sigma xx minus sigma yy by 2 sin of 2 alpha plus tau xy cos of 2 alpha. And then we also combined these two and developed a single equation, that is the equation of a circle which we call Mohr circle, and the equation is sigma n minus sigma average whole square plus tau n square is equal to r square. So, this is the equation of a circle. So, equation of a circle. So, this is the derivation that we discussed in our last class. Today, we are going to draw the Mohr circle. We will discuss how to construct the Mohr circle from this definition of 2D stress field, that we will see. Here sigma average is what? It is the quantity we have here, sigma xx plus sigma yy by 2. So, that is the sigma average. And what is r? That is the radius. This is square root of sigma xx minus sigma yy by 2 whole square plus tau xy whole square. Okay, so, our task is to draw the Mohr's circle for this 2D stress field, right. Okay, so, for that what we do, we first develop the axis. So, we have x axis and y axis. Let us draw the axis first. So, we have this is our x axis and then we also have y axis. Okay. Along x axis we plot axial stress and then along y axis we plot shear stress. Okay. Now, let us mark the two planes. So, this plane is, say we name it A, and this plane we mark it B. So, look at the A plane. What are the stresses acting? We have normal stress sigma xx and then tau xy. Now, if you recall our convention, if the stress acts on the positive plane, that means the normal along the positive direction, and the counterclockwise moment is in the positive direction of the, in this case, z axis, then we consider that stress to be positive. So, we have sigma xx and tau xy, both of them are positive. So, we will mark the point which defines the plane A. That we will do in a minute, but before that carefully look at this expression of equation of the circle. So, the center of the circle is sigma average comma 0, right. So, that is the center and the radius of the circle we have already identified. So, we have the center which is somewhere here. So, let us mark that this is the sigma average, right. Then our A plane is somewhere here. So, this is the point A. So, the coordinate for this point A is sigma xx and tau xy, right. And the distance between the center and this point is nothing but the radius. So, that is the radius. So, this is r, and let us mark this point sigma average comma 0, and we have this point, its projection on x axis shows sigma x, actually sigma xx, and this is our tau xy. Now, with the center and radius, we can draw the circle. So, we have the circle drawn where the point A is marked, and we can draw the complete circle. So, let us complete the circle and okay. So, where is this plane B? We can mark it. So, the B plane has two stresses acting, one is sigma yy and obviously tau xy. So, the coordinate of the B plane is given by this. So, we can mark it here. So, if we extend, obviously on the other side we can mark that. So, this is the point B, and if we take the projection, that point, here we have sigma yy and this is the tau xy. Now, why this tau xy we draw in the along the negative tau axis? Just look at the orientation and you can easily identify the reason. So, that is the graphical representation of the Mohr circle, and see the advantage of drawing this Mohr circle is from this 2D stress field here, we can actually draw this Mohr circle, we can immediately identify the center and the radius. So, we can draw this Mohr circle, and from this Mohr circle if we identify this point, say this point here and this point, these are the two planes along which we have only sigma and there is no tau. So, these are the points on the Mohr circle that represents the principal plane. So, this is sigma n, recall this is the maximum value, and here we have sigma n minimum value. Just note how easy it is to identify this principal plane from this Mohr circle. Not only this principal plane, we can also identify the plane along which the shear stress is maximum, which is here, because this is the maximum value of shear stress that we can see from the Mohr circle. So, this is tau n max, and carefully note that what is the magnitude of this maximum shear stress? This is nothing but r, which we also derived. Recall what is tau n max? This is sigma n max minus sigma n minimum divided by 2, which is nothing but the radius of the circle, right. So, if we know this point maximum sigma n and minimum sigma n, then if we subtract minimum from the maximum value, what we get is basically the diameter of this circle divided by 2 is the radius, which is the maximum value of shear stress, and that also we can identify from the Mohr circle easily. Now, what we earlier solved, if you recall, given a stress field, our task was to find out a plane at an angle alpha, and then what is the sigma n and tau n acting along that plane. We can also very easily identify. Let us first concentrate on the principal plane with respect to the plane A, marked A. So, we have, this is the point that marks the plane A, and here we have principal plane. Okay. So, the plane which is at an angle alpha in its original configuration will be at an angle of 2 alpha in the Mohr circle. So, you can see here it is 2 alpha always, right. So, we can start from this point A, and then if our plane makes an angle alpha in counterclockwise direction. So, we will go along that direction twice of alpha, and then we can identify the orientation of that particular plane. So, if this is twice of alpha, so this is basically the plane which makes an angle alpha in the original configuration. So, the moment we identify this point, we can drop the projection along x and y axis, and we can easily identify the corresponding sigma n and tau n. See how easy it is. Now, for this principal plane again we can follow the same notation. So, we can identify this angle, and then we can measure this angle. Half of that angle is originally the orientation of the maximum principal plane with respect to this point A. If you recall this, you can easily draw the Mohr circle from the given 2D stress field, and you can identify principal planes, you can identify maximum shear stress, you can also identify any plane at an angle alpha with respect to A, and then easily from this diagram you can quantify the corresponding axial stress and shear stress on the plane at an angle alpha. For the designer, this diagram is very handy because the moment you know this stress field, you first develop this circle, and then from that circle easily you can identify all the component stresses. Now, let us take an example. So, our first example is we have a 2D stress field So, sigma xx is equal to 60 MPa, sigma yy is equal to 20 MPa, then we have tau xy which is again 20 MPa. Now, our task is to find out sigma n max and tau n max. Okay. So, what we will do first from this given information? So, we can easily evaluate sigma average, that is 60 plus 20 divided by 2. So, average of sigma is 40 MPa. And then our next task is to evaluate R. So, this will be square root of sigma xx minus sigma yy by 2 whole square plus tau xy square. So, this is equal to square root of sigma xx is 60 minus 20 divided by 2 whole square plus tau xy square, which is actually 20. So, let us use 20. So, effectively if you do this 60 minus 20, this gives you 40 by 2 again 20. So, 20 root 2 MPa, and if you evaluate, this will be 28.3 MPa. Okay, so, what is the principal stress? Sigma n max. This is sigma average plus radius r. So, we can also find out minimum. So, if this is minimum, there will be a negative sign here. So, our sigma average is 40 plus minus 28.3, and if you work it out, it will be 68.3 as the maximum value and 11.7 is the minimum value. Now, for this principal plane, the orientation is tan twice alpha sigma n. If you recall, we derived this expression and it is twice tau xy divided by sigma xx minus sigma yy. So, tan of twice alpha corresponding to principal plane is nothing but 2 times tau xy is 20 divided by 60 minus 20. So, effectively this is 1. So, twice alpha sigma n is tan inverse 1, that is 45 degree. So, we have alpha sigma n is 22.5 degree. Now, our next task is to find out what is tau n max, right, and that we know it is nothing but radius of the circle, and we have already figured out this is 28.3 MPa. What is the orientation? Tan twice alpha tau n is equal to, if you recall, it is minus 1 by tan of twice alpha sigma n. That means, this is minus 1, and if you find out what is alpha tau n, this is nothing but tan inverse of minus 1. So, we will have 135 degree divided by 2, which is 67.5 degree. Now, let us cross verify. So, alpha sigma n minus alpha tau n, this is equal to the difference between these two angles, 22.5 minus 67.5. So, let us take the absolute value, and if you work it out, this is 45 degree. Obviously, that is the value between the principal stress and maximum shear stress that we derived earlier. Now, we will also see what is the meaning of this value in Mohr circle in a minute. So, what we do, let us quickly draw the Mohr circle for this problem, and then we can see what is the meaning of this difference between the principal stress and maximum shear stress. So, sigma xx is 60 somewhere here, and then 20 tau xy. So, we have this is the A plane. So, this is marked A, and sigma average will be somewhere here. So, if we draw the circle, it will, or let us just use a okay. So, what we have here, so this is our sigma n max, and this is our tau n max. Now, look at the angle between these two planes, this is 90 degree, and as you have earlier noticed that a plane which is in the original configuration of the 2D stress field, if it is at an angle alpha. So, here alpha is 45 degree. So, in the Mohr circle, it will be twice of alpha, which is 90 degree, and we can see that the angle between the principal stress and maximum shear stress is 90 degree in the Mohr circle. So, we draw the half circle. If required, you can also complete the circle, but this half circle provides us all the informations. What we need is principal stress and maximum shear stress. These are the two stress components that we need for design. Now, before we move to a different example, just let us go back to the Mohr circle once more, and let me show you one important aspect of the principal stress. Look at again this principal stress. So, the plane that experiences principal stress, it has no shear stress. Here tau is equal to 0, right. From the diagram we can easily quantify that. This is tau equal to 0 because it is exactly over the sigma axis. Now, look at this tau n max. At this point, so this is the plane along which we have maximum shear stress, but in this plane we have a non-zero axial stress. What is the value of the axial stress here? It is sigma average, and that is the most important thing to be noted. The plane that has maximum shear stress will have an associated axial stress, but the principal plane will not have any associated shear stress. Keep that in mind. Okay. And it is very easy to get that from the Mohr circle, otherwise you have to derive all these quantities and then see. Here it is clearly visible that the principal plane is exactly on the sigma axis, and hence tau is equal to 0, which is not the case of a plane where shear stress is maximum. There we have a finite value of the axial stress. Okay. So, let us take a different example, example 2. In this example, what we have is a stress field so sigma xx is equal to 80 MPa and sigma yy is equal to 20 MPa. Now, let us draw the Mohr circle for this configuration. Note tau xy is equal to 0. Okay, so, for this case we have sigma average is 80 plus 20 by 2. So, this is 50 MPa, and then r radius is square root of 80 minus 20 divided by 2 whole square, plus we have no shear stress. So, 0 square. Now, if you do this, you get r to be 30 MPa. Now, if you draw the Mohr circle, so we have one point here, that is the plane A, because it has no shear stress. So, this is sigma xx, which is 80 MPa, and then we have sigma yy, which is 20 MPa, and then average of that is here. So, if we can draw the Mohr circle, we can find out what is the tau n, right. So, this is 30. The point to be noted here is that the plane A is actually the principal plane, and here you have maximum value of the principal stress. Similarly, plane B, which is here, which will have the minimum value of principal stress. So, with that, let us conclude our discussion on principal stresses. I hope it is clear to you. If you have any query, please drop a mail and we will try to address it. Thank you very much.